the darkness was not absence. It was the pause before a breath. The moment before a thought becomes language. There were no stars, no time, no rhythm, only the absolute stillness of a silence that did not yet know it was silent. In that silence, something stirred. Not a spark, not even motion, just the possibility of becoming. And then, it began. Not with an explosion or a flash, but with the unraveling of non-existence into form. Space did not stretch into something that had once been empty. It was space itself that unfolded like a newborn wing, carrying with it time, temperature, and the tension of expansion. The first breath of being. In that instant, the universe bloomed not into stars, not yet, but into raw energy so dense it could not distinguish itself from itself. It surged outward faster than any particle could chase, a rush not of movement through space, but of space itself expanding. This was not like a fireball rising in the sky, but like an idea filling a mind that had only just been invented. Everything we know, atoms, stars, the breath you just took was still locked in potential. For the first 10 millionth of a trillionth of a second, there were no particles, only a sea of radiant tension, a field of quantum flickers where nothing held shape. Time ticked in intervals so small that the word interval loses meaning. But cooling brings structure, and as the young cosmos released its initial fever, it allowed the formation of the first fragments of form. Quarks jittered into existence, so restless they refused to be alone. Gluons danced between them, insisting on bonds that gave birth to protons and neutrons. This dance was violent and brief, and only in the narrowest window of temperature and timing could these particles hold hands long enough to matter. The air, though, there was no air thickened with interactions. From pure energy, from light itself, mass had begun to coalesce. These were not yet atoms. Electrons still soared too fast to be tethered, and light could not travel freely. The newborn universe was a clouded womb of charged particles, scattering photons like marbles across glass. If you had eyes in that fog, you would have seen nothing. If you had ears, you would have heard silence broken by the hiss of chaos. And yet something was beginning to change. Within those first few minutes, the universe cooled just enough for protons and neutrons to fuse. They created the simplest nuclei, hydrogen first, then helium, and the rare hint of lithium. This period, brief and irrevocable, stitched together the elemental thread from which all later complexity would be spun. The numbers, strange as they seem, still echo through the cosmos: 75% hydrogen, 25% helium, and traces so faint they barely whisper. These ratios were set not in stars, but in that primordial moment, when there were still no stars to shape or shine. The light that tried to escape could not. Electrons and photons collided endlessly, bouncing through a universe still too hot for stillness. But behind the fog, the orchestra was tuning. With every passing heartbeat of cosmic time, the temperature dropped, and the first outlines of permanence began to trace themselves into being. Soon, the forces that govern everything would begin to separate, each peeling away from the original unity that had once bound them. Gravity, the weak and strong nuclear forces. Electromagnetism, once indistinguishable, would take on distinct roles. Their divergence was not a collapse, but a kind of crystallization, like water freezing into geometric symmetry, defining shape and direction where none had existed before. And so, from a nothing that was not truly nothing, a universe took its first steps into becoming, not with thunder or light, but with quiet laws unfolding in a darkness too dense to allow vision, a darkness not of absence, but of infinite potential yet unshaped. 1,000,000 years might pass without a single sound if there is nothing to carry it. After the first 380,000 years, silence in the early universe was no longer just a metaphor. It was a physical reality. As the newborn cosmos exhaled its heat into ever-expanding space, its temperature fell below a threshold that allowed electrons, for the first time, to slow and settle into orbit around the nuclei that had formed long before them. The particles that had wandered like restless ghosts finally found their place, and from this delicate embrace, the first atoms emerged. That union did not merely create matter, it changed the very transparency of the universe. Light, once trapped in an endless ricochet of collisions, was suddenly released, and with it came a new kind of clarity. Photons poured into the openness, stretching and fading as space expanded, leaving behind a faint glow, a whisper of the infant cosmos that still surrounds us in all directions. This is the cosmic microwave background, the earliest light we can detect, not because it was the first, but because it was the first allowed to travel freely. Yet even with the birth of atoms and the liberation of light, the universe had no stars. The sky was dark, though not empty. It was filled with potential, with hydrogen and helium clouds drifting through space like scattered ash, remnants of a fire whose embers had not yet reignited. This was the age of silence in a different form the time cosmologists call the Dark Ages, not because there was no activity, but because the light had not yet returned in new forms. Invisible threads of gravity began to tug gently at the vast sheets of gas. In some regions, matter clumped just slightly more densely than in others, and these tiny differences grew steadily over hundreds of millions of years. The universe was laying down a kind of scaffolding, invisible and immense, an intricate web upon which future galaxies would hang like dewdrops. There were no galaxies yet, no suns, no planets or moons, just darkness, and the slow tightening of gravity's fingers. Eventually, in these dense knots, clouds began to contract. As they collapsed under their own weight, the temperature at their centers began to rise. Pressure mounted, and then, quietly and invisibly, fusion was born. The first stars lit up like flares in the abyss. They were nothing like the stars we know, massive, short-lived, and unpolluted by the complex chemistry that defines our solar system. These were elemental furnaces, raw and primitive, composed almost entirely of hydrogen and helium. They lived fast and died violently, burning through their fuel in only a few million years. Their lives were short, but their deaths rewrote the cosmos. In their cores, under unimaginable heat, they had forged new elements: carbon, nitrogen, oxygen, pieces of a puzzle that had never before existed. When they exploded as supernovae, they hurled these creations into space, seeding the vast darkness with materials that would one day form planets, oceans, blood, and thought. The violence of these first explosions did not end in destruction. Their shockwaves compressed nearby gas clouds, triggering the birth of new stars, each formed from matter more complex than the last. A lineage had begun, a cosmic ancestry of stars, each generation inheriting a richer chemical legacy than the one before. But that was still in the future. In the universe's early years, every new light that flared to life pushed back the darkness just a little more. As ultraviolet radiation from these ancient stars poured into space, it began to tear apart the hydrogen atoms that filled the void. Photons stripped electrons from protons, reionizing the universe, and in doing so, ending the cosmic dark ages. The universe, once dim and unformed, now shimmered with a growing lattice of starlight. Galaxies began to coalesce at the nodes of the cosmic web, spinning into spiral arms and elliptical clouds, dancing to the rhythm of gravity. What had begun as chaos had turned toward order, not because it was designed, but because the rules were written in the fabric of space and time. Still, nothing about this unfolding was predictable in the way we often imagine inevitability. If quantum fluctuations had danced just slightly differently, the stars we know, the planets we stand on, might never have formed. Our entire cosmic structure balances on the edge of these ancient uncertainties, ripples in the vacuum that inflation magnified into the framework of everything. A strange irony persists: the cold silence after the Big Bang had to last for hundreds of millions of years before heat and light could return in meaningful form. Before the sun could rise, the universe had to rest. Before atoms could bind into molecules, the space between them had to cool. In this long pause, the stage was set, not by force, but by the absence of it. And then, one star became many. One cloud gave rise to a cluster. One explosion echoed into dozens. And from this silent beginning, the sky learned to sing. The quiet chorus of stars, once scattered and few, began to crescendo into constellations of complexity. Galaxies, spun into being by the invisible architecture of dark matter, turned slowly in space, their spiraling arms cradling billions of suns. These spirals were not perfect or pristine. They grew through violence. Gravity, indifferent to the scale of suffering, pulled smaller galaxies into the bellies of larger ones. The sky itself became a history of collisions. Each encounter was both destruction and genesis. When galaxies merged, stars were flung into elliptical halos, gas clouds compressed into newborn clusters, and supermassive black holes at their centers edged closer, eventually coalescing in silence too deep for sound. These central black holes, once just strange theoretical outcomes of general relativity, became cosmic engines. As matter spiraled toward their event horizons, it heated and screamed in high-energy light, illuminating the cores of galaxies and powering quasars that shone more brightly than entire clusters. But even their brilliance could not overcome the strange truth that most of what exists does not shine. As telescopes reached further into the cosmic past, as instruments strained to measure gravitational pull versus visible mass, astronomers began to suspect an absence so massive it reshaped their understanding of presence. Stars spun in galactic disks faster than gravity from visible matter should allow. Something unseen was holding them together. Dark matter. Not because it is black or even shadowed, but because it neither absorbs nor emits light. It is invisible to every wavelength we know, detectable only by its gravity. It may outnumber normal matter by a factor of 5. It surrounds galaxies like a cloak and forms the very scaffolding upon which all visible structure is hung. It does not collide, does not clump into planets or stars, does not burn. And yet it is what allows the night sky to exist at all. Then there is the deeper silence, still dark energy. Unlike dark matter, which pulls, dark energy pushes. It is not a force we can localize or isolate. It permeates space itself, a kind of pressure written into the void. In the late 20th century, astronomers measuring the light of distant supernovae discovered something that stunned the field. The expansion of the universe was not slowing as expected, but accelerating. This defied centuries of assumptions. Gravity, even on cosmic scales, was expected to act as a brake, gradually slowing the outward rush born from the Big Bang. Instead, the galaxies are speeding away from one another faster with time, carried by a space that seems to stretch more eagerly the more it expands. No one fully knows what dark energy is. Some think it is the cosmological constant, a fudge factor Einstein once inserted into his equations and later called his greatest mistake. Others imagine it as a quantum field, fluctuating with the fabric of space-time. And still others wonder whether it is a sign that our understanding of gravity is incomplete at the grandest scales. Whatever its nature, its implications are clear. The fate of the universe may not be a gentle coasting or a collapsing return. It may be an eternal, accelerating separation. In time, galaxies beyond our local group will speed so far and so fast that their light will never reach us again. The night sky, once full of stars, will become a smaller and smaller window into a shrinking past. Even light itself is not eternal. Photons from the cosmic microwave background continue to stretch, their energy fading with every heartbeat of expansion. One day, even that background glow may fall below detection, and the record of the universe's birth will vanish from view. This accelerating drift is not a tearing or breaking. It is the absence of grip, the emptiness of distance growing too fast to be bridged. And though the galaxies still dance, though stars still burn and die, there is a slow inevitability building in the background, the quiet extinguishing of connection. We live in a golden age not because our time is special in its content, but because we can see. We are early enough that the echoes of the beginning still wash over us. We can study the birth of time, map the expansion of space, and trace the fingerprints of invisible forces. But this window will not stay open. The past is not only behind us, it is also fading. And so the stars remain, for now, as reminders of a universe that once burst from nothing into brilliance, that once seeded its silence with the raw ingredients of life. Their light crosses unimaginable distances to find us. But in the far future, the silence will grow again, not from absence, but from distance untraversed, light undelivered, and stories untold. A planet coalesced from dust and ash in the outer spirals of a medium-sized galaxy. Third from a yellow star, it spun without language for billions of years, collecting the minerals and elements flung outward by generations of dead stars. Carbon, forged in ancient cores. Iron, birthed in supernovae. Oxygen and nitrogen, drifting freely in interstellar clouds before gravity sculpted them into air and ocean. There was nothing inevitable about the shape it took. Seas did not have to form. Atmosphere did not have to hold. Life did not have to arise. But chemical restlessness danced across clay and hydrothermal vent, and eventually, patterns emerged that could make copies of themselves. Simple at first, then layered, folded, armored, motile. Complexity rose, not in a straight climb, but in fits of catastrophe and reinvention. Through extinction and mutation, intelligence emerged, not as a trait, but as an accident of survival. On this single planet, in this modest corner of the cosmos, matter began to wonder about itself. Eyes turned upward not just in fear or navigation, but in curiosity. Something in the minds shaped by starlight began to ask what stars were. That question took millennia to articulate, and longer still to answer. Eventually, tools of glass and steel were pointed at the sky. Telescopes extended the eye. Accelerators cracked apart the smallest pieces of the known. Mathematics began to uncover rhythms hidden beneath the visible, and slowly, the universe started to explain itself through the minds it had unwittingly produced. But in that very effort, noble, wondrous, there came a growing awareness of limits. The more we learned, the more fragile the known became. The constants of nature were not merely numbers. They were balances on a razor's edge, the strength of gravity, the charge of the electron, the density of dark energy, each tuned within narrow margins that permit galaxies, stars, chemistry, breath. If gravity were slightly stronger, stars would burn out in moments, collapsing into black holes before life could find a foothold. If it were slightly weaker, matter might never have clumped, leaving a universe of eternal fog. The ratio of forces, the timing of phase transitions, the presence of matter at all, none of it demanded by logic. All of it balanced so precariously that some began to wonder whether such precision could be coincidence. From that doubt arose the anthropic principle, not as theology, but as contemplation. Perhaps the universe appears tuned for life, because only a tuned universe allows observers to arise at all. There could be many universes, infinite or near so, each with different laws. Ours would then be unremarkable, just one bubble in a sea of failure and silence, where finally, the music played long enough to listen to itself. This idea leads to the multiverse, not a fantasy, but a theoretical consequence of inflation, quantum mechanics, or string theory, depending on the path taken. In some versions, new universes bud off from quantum fluctuations like dew on a spider's web, each isolated and unreachable. In others, our own universe exists on a brain floating in a higher dimensional space, colliding now and then with others like it, triggering new cosmic births. None of these are proven, but all are consistent with the mathematics that describe the world we can test. The more we try to locate our position in the cosmic order, the more the ground shifts beneath us. We may not be the center. We may not be unique. We may not even be necessary. And yet, the very act of imagining these possibilities is a kind of defiance. It is not comfort we seek, but clarity. If the universe is a rare bloom in a field of lifeless variables, then to know it even briefly is to hold something sacred, even if that word belongs more to poetry than physics. There is a kind of quiet reverence in realizing that we live not under a dome of stars, but inside a storm of probabilities that, for a while, permitted reflection. The night sky is not a ceiling, but a question, and we are the echo of that question trying to answer itself. Somewhere, deep in the cosmic distance, a galaxy is vanishing, not because it is collapsing or consumed, but because the space between it and us is expanding faster than its light can travel. It continues to exist, burns with stars, carries the momentum of a billion years of history, but its story is now forever beyond our reach. The night sky, so vast and generous in our time, is slowly losing its memory. In the far future, this quiet disappearance will become the norm. Galaxies will drift beyond the cosmic horizon, leaving behind only the local group, those few dozen that remain gravitationally bound to us. Beyond that, silence will thicken. The cosmos will not end in a crash or a fire, but in a soft dimming, like the last embers of a great fire cooling into blackness. The stars will age. Red dwarfs, the most enduring, will flicker for trillions of years. But even they will one day exhaust their fuel. White dwarfs will cool into black cinders. Neutron stars will spin their last. Black holes, the most patient objects in existence, will slowly evaporate through Hawking radiation, particle by particle, until even their mass becomes memory. What remains will not be empty in the way we think of it. It will be thin, cold, and vast. A universe where energy is so diffuse that no new complexity can arise. A place where every possibility has already played out, and no reset is coming. This scenario, known as the heat death, is not merely a theoretical curiosity. It is a natural consequence of entropy, the tendency of energy to spread, of structure to dissolve, of time to move only forward. And yet, it is not entirely bleak. For in this long, slow twilight, meaning is not dictated by duration. It is forged in the moments where perception exists. In the rare span when stars burn and minds awaken, when questions are asked and answers sought not to dominate, but to understand. We are of this universe, not merely in it. Our atoms were fused in stars. Our thoughts are electrochemical echoes of ancient energy, rearranged by biology into something that can doubt and wonder. Even if our kind disappears, even if the species vanishes long before the last light fades, that we existed at all reshapes the universe's story. Perhaps this, too, is a kind of cosmological inheritance, that from the laws that shaped stars and galaxies, something arose that could look back at those laws in awe, not because we were intended, but because we became capable of interpretation. And in interpretation, there is agency. In wonder, there is resistance to silence. Even now, in this era where the universe is still legible, we begin to build instruments not just to look, but to listen more deeply. We send spacecraft beyond the reach of our sun, messages carved in gold and digital pulses, hoping that someone, somewhere, someday, might hear and reply. Not because we expect them to, but because we can. This act of asking across impossible distances, of waiting with no assurance, is the most human kind of hope. It is not naive. It is not desperate. It is simply the echo of awareness refusing to be still. If one day, on a world we'll never see, a mind will never meet points an eye at a cooling remnant and deciphers its origin, they will find traces of us in the dust, not as conquerors, not as footnotes, but as part of the unfolding a voice that rose briefly, and spoke, and listened, before returning to the dark from which it came.
You are not merely floating in space. You are suspended on a membrane of perception. Behind you lies the echo of human history, a chorus of myths, physics, telescopes, and equations. Before you, only a silence that has never been broken. You take a step forward, not with feet, but with thought, into the outermost question. Where does existence stop? And if it doesn't, if it simply stretches forever, what, then, does that even mean? The concept of the edge of the universe is both ancient and entirely modern. It haunted the imaginations of early mapmakers who inked dragons into the margins of the known world, and still haunts cosmologists armed with supercomputers. But today, the dragons have been replaced by quantum fields, dark energy, and thermodynamic paradoxes. And the boundary, it's no longer a place, but a limit of perception, a moving frontier called the observable universe. Here's the catch. It's not the cosmos that ends, but our ability to see it. The observable universe spans about 46 billion light years in every direction, not because that's how big the universe is, but because that's how far light has managed to travel since the Big Bang, stretched by the accelerating expansion of space. When you look At a galaxy 10 billion light years away, you're not just seeing distance, you're seeing time itself unspool. You're peering into the past, but this horizon is not static. With every tick of the cosmic clock, the boundary of what we can observe grows by another light day in every direction. Yet the farther we look, the deeper into time we sink. Until we approach a wall, we cannot cross the cosmic event horizon. It is not built of atoms or photons. It is woven of time and motion. Galaxies beyond this horizon are receding faster than the speed of light due to cosmic expansion. Not because they're violating relativity, but because space itself is stretching. Imagine being at sea, on a boat with no oars or engine, watching the shore slowly disappear, not because you are moving, but because the ocean is growing between you and everything else. Eventually, that shore fades from view forever. That is our future, with distant galaxies. The cosmic event horizon defines the farthest edge of our reach. Anything beyond it, stars, galaxies, even entire superclusters, can never influence us, no matter how long we wait. And in a future ruled by accelerating expansion, this horizon will shrink relative to the cosmos. One by one, galaxies will vanish from our view. In 1 trillion years, only the nearest galaxies in our gravitational group may remain visible. The universe will seem lonelier, simpler, and more static, not because it is, but because we'll have lost our window into its depth. This unfolding isolation forces a disturbing question. Will future civilizations know they're alone simply because their telescopes cannot see far enough? Would they assume that the universe is small, static, and finite, because the evidence of its vastness has fled beyond their sky? In that sense, we are living in a cosmological golden hour, perched on a rare moment when we can still see the afterglow of creation and the fingerprints of distant galaxies. But even now, there are shadows on our cosmic map, places where our theories fail to light the way. The theory of cosmic inflation offers one such illumination. In the first split second after the Big Bang, the universe expanded exponentially, faster than light, not as a violation of Einstein's rules, but because those rules apply to matter moving through space, not to space itself. This sudden, incomprehensible expansion smoothed out wrinkles in the early cosmos, stretched microscopic quantum fluctuations into the seeds of galaxies, and gave the cosmos its apparent flatness. Flatness is a strange property. In a curved universe, light would travel in arcs, and triangles wouldn't add up to 180 degrees. But our universe, on the largest scales, seems almost perfectly flat. Cosmic inflation explains why, much like zooming in on a balloon until its curvature disappears, inflation blew up the early universe so massively that any curvature was diluted to invisibility. The implication, what we call the universe, our observable slice, is likely just a bubble in an ocean of space. That ocean, known as the inflationary multiverse, may be birthing new universes constantly. In other inflating regions far beyond our horizon, each bubble could contain different physical laws, different kinds of matter, perhaps even different notions of logic or causality, and we, like fish in a cosmic aquarium, can never peer outside our bubble to see the others. This isn't just poetic speculation. The mathematics of inflation, when taken to their logical conclusion, lead directly to the idea that the universe may be far larger and more diverse than we can observe. And if inflation is eternal, as some models suggest, it may mean that the universe has no global edge at all, just an infinite foam of pocket worlds endlessly inflating. In such a framework, the very notion of a universe is outdated. We would need to redefine existence itself not as a singular event or realm, but as a multiversal process, a field of possibility, blooming without beginning or end. But there's something sobering in this grandeur. If universes are so easily spawned, then what makes ours special? Why does it contain life, consciousness, memory, and dreams? Here, the idea of fine-tuning enters. The constants of our universe: gravity, electromagnetism, the mass of particles are delicately balanced. A slight variation, and atoms wouldn't hold, stars wouldn't ignite, chemistry wouldn't unfold. If there are infinite universes, then perhaps we simply live in the one where life can exist, a cosmic lottery, where winning is rare, but inevitable, given enough tickets. And yet, even if this multiverse is real, we cannot see it. Our observable bubble remains our only lighthouse in a sea of eternal darkness. We search its edges with instruments tuned to the oldest light, the cosmic microwave background, the afterglow of the moment when the universe became transparent. This light, a relic of 380,000 years after the Big Bang, is nearly uniform, yet its faint ripples reveal the fingerprints of quantum randomness writ large by inflation. These ripples seeded galaxies and shaped the cosmic web. They are a bridge between the micro and the macro, between vacuum fluctuations and the grandeur of galactic clusters. But even here, at the limits of what we can observe, strange anomalies whisper, cold spots, asymmetries, potential signatures of a collision with another universe, bruises from a multiversal birth. Diversal. Whether these are artifacts or evidence remains unknown, but they hint that the veil of our cosmos may be thinner than we imagine.
What, then, lies beyond blue?
Not dragons or angels, but something perhaps more terrifying. The unknown that obeys different rules. A vacuum that births universes. A dimension in which time is not linear, space is not three-dimensional, and identity itself is an illusion. The edge of the universe is not a wall, but a philosophical crisis. It forces us to confront the fragility of knowledge, the arbitrariness of perspective, and the humility demanded by the cosmos. As we drift deeper into this realization, one truth becomes clear. The boundary we speak of is not out there. It is within us, in the limits of our comprehension, our language, our tools. And yet, we press forward, drawing constellations across the abyss. Imagine awakening, not to a sunrise, but to a planet unfamiliar in shape and sky, yet still Earth. A world where the continents are strangers, where the wind tastes of minerals never catalogued, and the stars above cast a different constellation across a breathable dusk. This is not science fiction. This is Earth 2 billion years ago. The terrain was silent then, at least to human ears. The forests, deserts, and rivers we know did not yet exist. What lived and moved across the surface bore no resemblance to us. In the shallows of warm oceans, microbial mats breathed out oxygen, slowly reshaping the chemical fate of the planet. This was the time of the Great Oxygenation Event, a planetary metamorphosis that would ultimately make higher life possible. It's here within this alien, ancient Earth that the question sharpens. Could intelligence have sparked, flared, and vanished long before we emerged? At first glance, the answer seems absurd, but only because we look backward through the lens of our own history, as if intelligence is fated to wear a bipedal body, to build cities, to reach for the stars. But perhaps that's an illusion, born of proximity. Evolution does not plan, it meanders, leaps, stumbles. And time is vast enough to allow many different walks of fate. The Silurian hypothesis, introduced by climatologist Gavin Schmidt and astrobiologist Adam Frank, dares us to consider this. They posed not a claim, but a question. If an advanced industrial civilization had existed in the deep geological past, would we be able to detect it today? Their answer may be, but only barely. Geological time is not generous. The Earth is a master of self-forgetting. Over millions of years, tectonic plates churn the crust. Over hundreds of millions, entire mountain ranges rise and erode. Over billions, continents shift, oceans vanish, and every surface memory is sanded down to oblivion. The longer back you go, the fewer traces survive. Concrete crumbles within thousands of years. Metal corrodes. Plastics, though durable on human timescales, degrade over millennia. Even nuclear waste decays into geological neutrality in less than 1 million years. If a civilization had risen on Earth 1 billion years ago, its cities would be gone. Its machines would be atoms. Its monuments, if any were built, would have been ground into anonymous sediment. But not everything disappears. Some scars go deep. The Silurian hypothesis focuses on technosignatures, geochemical footprints left by industrial activity, a sudden spike in carbon dioxide, an anomalous mix of heavy metals, isotopic shifts in marine sediments. All these could betray the presence of large-scale technology, even if we cannot identify the tools. Take our own industrial age. In just 2 centuries, humanity has already left a planetary fingerprint. Fossil fuel combustion has shifted atmospheric carbon ratios. Plastic particles now reside in every ocean. Rare earth metals, once buried deep underground, now lie dispersed across continents. Nuclear detonations have seeded the atmosphere with radionuclides that will persist for tens of thousands of years. From a future geologist's perspective, these could be read as the signal of intelligent life, even if no fossils, no buildings, no machines remained. But here lies the challenge. How do we distinguish natural anomalies from intelligent ones? Nature is a superb engineer. Volcanic eruptions can alter climate. Meteorite impacts can disperse rare elements. Natural nuclear reactors, like those found in Oklo, Gabon, can mimic human designs through pure coincidence. This ambiguity makes deep-time archaeology a game of shadows. Every clue must be balanced against simpler explanations. And yet some anomalies continue to whisper. Consider the Paleocene-Eocene thermal maximum, a dramatic spike in global temperatures about 55 million years ago, linked to a massive release of carbon. The source remains debated. Methane clathrates volcanic activity, or something else entirely. The geological record does not speak plainly. Then there are strange isotopic excursions, abrupt shifts in marine chemistry, and inexplicable concentrations of certain metals in ancient strata. Singularly, they are oddities. Collectively, they are a pattern that dares interpretation. But perhaps the most intriguing idea isn't that we're missing evidence, but that we're missing what evidence should even look like. What if an ancient civilization didn't burn coal, didn't smelt metals, didn't build with stone? What if its technology was biological, its tools engineered from living tissue? What if it communicated not with radio waves, but with biochemical emissions or neural resonance? Would such a society leave behind any trace that modern geology or archaeology could interpret? The answer may well be no. It's a chilling realization that the vastness of geological time doesn't just erode stone, it erodes intelligibility. After 1 billion years, not only would a city vanish, but the very concept of the city might leave no footprint at all. Yet we continue searching. Why? Because the idea that we are the first and only intelligent beings to evolve on Earth carries an uncomfortable weight. It assumes rarity where time has offered abundance. It assumes a straight line where nature draws spirals. And if we are not alone in Earth's history, if there were others before us, then we must also face the second question. Why did they vanish? Perhaps they self-destructed. Perhaps they transcended matter. Or perhaps they simply passed a threshold. We have yet to approach a technological or ecological bottleneck that defines the lifespan of all complex societies. There's also the unsettling possibility that intelligence isn't favored by evolution, but rather tolerated briefly before its side effects entropy, imbalance, collapse selected out. This invites a haunting reframing. Intelligence may be an anomaly, not a pinnacle, a fleeting combustion in the slow oxygenation of a planet, a pattern that burns brightly and then vanishes, leaving only subtle discolorations in stone. And still, We hope. Because hope is itself a form of memory, a reaching back, a reaching forward in a small core drilled from ancient rock. A geologist may one day detect a technosignature, an isotopic quirk, a mineral out of place, a chemical rhythm unlike any seen before. It won't be proof, but it will be a voice, faint and distant, speaking across time. You drift away from Earth, leaving its noise behind, as you float through a cosmic sea emptied of light. In this quiet, you begin to ask, where is everyone? Not just now, but always. The silence between the stars speaks louder than any signal. Imagine ancient civilizations, light years away, that might have risen and fallen long ago. Their radio beacons, once powerful, now fade into cosmic static. Perhaps they never mastered broadcasting into the void, or their light was extinguished before their reach could cross the gulfs. You wonder, did they even live long enough to build a cosmic signal? This leads to a deeper, unsettling puzzle. The Great Filter. Somewhere in the sequence from inert matter to star-faring intelligence lies a barrier. It may be ahead of us, or behind us. If behind, perhaps thousands of civilizations were extinguished before ever escaping their homeworld. If ahead, we might be flirting ever so dangerously with our own threshold. The silence of the universe could be the echo of filter past or a silent caution of filter future. Next, consider what intelligence might look like elsewhere. Not humans in alien skin, but minds that evolved under extreme conditions, on freezing rogue planets, inside crushing gas giants, or far beneath ice-bound oceans. Their intelligence might be post-biological, born not of flesh and blood, but of silicon, quantum fabric, or patterns of pure information. Such beings may communicate not through waves, but through the migration of data, hidden in gravitational ripples or the structure of dark matter. And if their form is so radically different, how could we even recognize them? Let your mind drift to stealth civilizations, beings who chose silence, who hid behind the cosmic curtain. Maybe they knew the danger of revealing themselves in a hostile universe. Perhaps they cloaked their megastructures, masked their emissions, even submerged themselves in virtual realities to avoid cosmic predators. What we call silence might be intentional discretion, a strategy for survival. Then there's the alluring but unnerving idea of the simulation hypothesis. Perhaps our universe is an artificial environment, a sandbox in which intelligences far more advanced than us conduct their experiments. If so, the absence of contact isn't cosmic loneliness, it's deliberate design. We could be the data points in a larger study, the chosen subjects of an experiment, or an art piece that stretches across dimensions we cannot perceive. It's as though you're an archaeologist of absence, trying to reconstruct civilizations from the gravestones of silence. But here's the paradox. What if intelligence inevitably vanishes? What if complexity itself triggers collapse? Every technological leap brings resource depletion, environmental risk, entropy, leading to implosion before expansion. Intelligent life might be universally self-limiting, a cosmic pattern written into the laws themselves. Or perhaps we're looking in the wrong period. What if cosmic civilizations left their mark millions or billions of years ago, and their signatures have dissipated into background radiation, cosmic dust, or quantum noise? If they existed in the deep past of the cosmos, long before Earth formed, their legacy might be gone or nearly invisible today. Now imagine this. You're not biased by biology. You're a quantum consciousness, evolving inside a black hole's event horizon, or a sentient interstellar cloud of plasma. Your awareness spans centuries in a single thought, yet you leave no footprints, just subtle perturbations in the curvature of space-time. Would we see you? Would we know such existence even counts as life? And yet, the silence could also be a canvas, a space awaiting discovery. Maybe we're just the first to reach out, the first to design probes or unleash gravitational pulses with universal reach. If so, our moment is also an invitation. Should we define cosmic conversation? Should we build not just telescopes, but ethical protocols? Could the ultimate question be, who do we become if we choose to speak across the void? You sense that even the question is a gift. To wonder is to light a spark. To ask is to step beyond Earth's cradle. And perhaps, somewhere in that silence, someone or something is also wondering. Your awareness shifts now to the fabric of space-time, not just the contents of the cosmos, but the currents and textures that shape everything. Imagine drifting through an interstellar river, where gravity's ripples carry the story of every massive object in motion. Black holes, neutron stars, and galaxies all contribute to the tides, sending gravitational waves, faint yet far-reaching murmurs that we are only now learning to detect. Remember LIGO's first detection in 2016, two black holes, each tens of times the sun's mass, spiraled together and merged. The signal lasted only a fraction of a second, but that brief chirp passed through Earth, carrying encoded tales of the object's mass, spin, and final fate. It was the universe whispering, revealing something deeply fundamental, something previously undetectable by light or telescopes. In a sense, each gravitational wave we detect is like eavesdropping on a cosmic dialogue that spans billions of years. Now, picture the magnetic fields threading through galaxies immense, invisible tentacles shaping gas and dust, guiding star formation, even influencing the path of cosmic rays. These fields are relics of the early universe, evolving over eons. They speak of processes, yet wholly understood, a cosmic memory woven into the darkness itself. Your senses turn inward now, into the bizarre realm of the quantum vacuum, where even empty space teems with fluctuating energy. These ephemeral bubbles of virtual particles are fleeting but fundamental, giving rise to real consequences like the Casimir effect, where two metal plates find themselves mysteriously drawn together by vacuum fluctuations. These currents of the vacuum might hold keys to uniting gravity with the quantum world a door into realms beyond our current cosmology. But you don't linger there. The tide drifts you outward again, toward the edges of the cosmological canvas, where dark matter lurks. We cannot see it, but we feel its weight. Without it, galaxies like our Milky Way would tear themselves apart, stars flung into the void. Surveys of galaxy clusters show us that the majority of matter is unseen silent halos around galaxies, vast filaments in the cosmic web, structures that anchor the luminous islands of stars in space. Even more enigmatic is dark energy, the silent accelerator that pushes galaxies apart. It permeates space itself, an invisible current stirring the cosmic sea, changing its destiny. Its nature remains obscure. Vacuum energy, a field yet unknown, a misread signal of gravity's breakdown on the grandest scales. As you drift through these forces, gravitation, magnetism, quantum fluctuations, dark energy, you sense the unity hidden beneath. These are threads in a grand tapestry that connect the smallest subatomic world to the vast cosmic web, where monumental gravity collides with quantum whispers, where geometry and entropy meet. There lies the frontier of human understanding. And don't forget the cosmic microwave background, the oldest light. It carries within it minuscule ripples, seeds of every galaxy, cluster, and void. Its slight temperature variations map the ancient patterns laid down by inflation. Perhaps hidden in those fluctuations lie the signatures of forces we have yet to comprehend, echoes from beyond our cosmic horizon. Your drift continues to the concept of cosmic topology, the global shape of the universe. If space is curved back on itself, you could travel light years in a straight line and return to your origin, haunted by echoes of your departure. Scientists are testing this by searching for repeating patterns in the cosmic microwave background, looking for the hall of mirrors that would reveal a finite, folded cosmos. Yet all of this, these waves, these fields, this dark scaffolding, these are stories of underlying structure. But what if structure itself is emergent? Some theoretical physicists suggest that space-time might not be fundamental at all, that it could arise from entanglement, information networks, or quantum bits. The fabric of reality could be a projection of more fundamental information patterns. If so, maybe what lies beyond the universe is not space, but the layer below networks of quantum entanglement, pre-space-time code from which our cosmos is woven. As the journey nears its current crest, you sense a subtle tension between what we know and what we can imagine. We've stepped from black hole mergers to vacuum fluctuations, from gravitational waves to cosmic topology. These elements are our atlas of the unknown, guiding both our instruments and our imagination. You float now at the intersection of matter and mind, where galaxies' grandeur meets the enigma of consciousness. Amidst the cosmic web's network of dark matter and radiation, life finds a foothold. Tiny, improbable sparks of organization in a sea of entropy. Molecules assemble into cells, cells into brains, And somewhere along that long journey, awareness awakens light piercing the dark from within. Think of a neuron in your brain, communicating through electrical signals. These firings are echoes of cosmic processes, waveforms traveling through fields, energy transferring along gradients. Within us, space-time and quantum rules collaborate to create a coherent self. Our perception is not separated from the universe. It is woven into the same fabric. But what does it mean to carry awareness in a universe written largely in mathematics and symmetry? Human minds have begun to translate the stars into equations, expressed the cosmic origin of matter in particle colliders, and glimpsed the early universe in snapshots of the cosmic microwave background. Our consciousness has become a lens, focused backward in time, letting us touch and perhaps shape the very moment of creation. Yet awareness also brings paradox. You understand that every structure from atoms to galaxies is subject to entropy. That complexity is temporary. Civilizations rise. Quasar jets light up once dead galaxies. Black holes decay. Conscious beings like us are fragile players in cosmic time. Our ephemeral spark begs the question, is intelligence just a flash, doomed to fade like a supernova, or part of something larger, something cosmic? If life is woven from cosmic threads, perhaps consciousness itself could be universal, an emergent property of certain complex systems under the right conditions. In that case, wherever the cosmos has organized matter into self-reflective patterns, whether under earthly oceans or distant exoplanets, there might be communities akin to ours, asking versions of these same questions. Imagine a distant intelligence that observes its cosmic microwave background, hears its own gravitational waves, surveys its dark, energy-dominated future. Perhaps they have mapped their cosmic topology, theorized multiple universes, or speculated on the holographic nature of reality. Yet, they may remain cut off from others by the event horizon, each consciousness stranded in its own observable bubble. That loneliness deepens the philosophical stakes. If every observer is confined to their local horizon, if space itself, and perhaps time itself, is fundamentally emergent, then each intelligence may be writing a story that starts and ends within its own bubble of space-time. Communication across these bubbles might be forever impossible, but the impulse to reach beyond, to decode the boundary, to uncover what lies outside our horizon, is a powerful testament to intelligence itself. It drives us to build space telescopes, to detect primordial gravitational echoes, to send messages into the void in the hope someone or something will listen beyond the cosmic horizon. None of us yet know whether those signals will ever find another listener. But the act of asking, of probing, deciphering, imagining may be the most cosmically significant thing a mind can do. In gazing outward, we reflect on ourselves. In seeking the origin, we confront our mortality. In tracing the fate of stars, we trace the fleeting arc of our own existence. So, as you settle into silence, Picture the universe stretching behind you, ancient and vast. Then, picture yourself an observer born of quantum dust, casting a question across the cosmos. What lies beyond? The answer may be forever beyond reach. But the question matters. It binds us to the universe and to each other. And perhaps, in that shared wonder, lies a deeper kind of connection beyond space, beyond time, beyond all we know. Let this final note linger in your mind. Sleep gently closes around you. You have traveled across space-time's deep rifts, from inflation's birth to cyclic futures, from quantum voids to the emergence of awareness. You have touched the edge of the cosmic boundary and found not emptiness, but invitation. And in your question, the cosmos finds its echo.
In the vast darkness of space, a single galaxy burns bright enough to rewrite everything we thought we knew about cosmic history. This galaxy existed when our universe was barely 290 million years old, just 2% of its current age. But this ancient light carries secrets that challenge our deepest theories about how galaxies form, how quickly stars can ignite, and whether the universe itself might be hiding inside something unimaginably vast. From impossible brightness to missing black holes. From chemical fingerprints that should not exist to theories that place our entire reality within a cosmic prison. Prepare yourselves. Deep in the constellation Fornax, astronomers discovered something that should not exist. A galaxy that burns with the light of hundreds of millions of suns. Yet it formed when the universe was barely out of its infancy. Named Jade's GS Z14-0. This cosmic lighthouse shattered every distance record we had ever set. At a redshift of 1432, it dates back to less than 300 million years after the Big Bang, pushing our view deeper into time than ever before. To understand how extraordinary this discovery truly is, picture the universe as a 13-year-old child. This galaxy would have existed when that child was barely 3 months old. The light we see today began its journey across 13.5 billion years of expanding space. Stretched and reddened by the universe's own growth, the James Webb Space Telescope observed this galaxy for almost 10 hours using its near-infrared spectrograph. And when scientists first processed the spectrum, they knew they were looking at something unprecedented. The previous record holder, another galaxy discovered just years earlier, suddenly seemed almost modern in comparison. But distance alone was not what made this discovery so startling. Jade's GS Z14-0 is over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from emission near a growing supermassive black hole. For a galaxy this early in cosmic history, such a size defies our expectations. Imagine trying to build a massive city in just the first few days after breaking ground on an empty plot of land. That is essentially what this galaxy accomplished in cosmic terms. The building blocks of matter had barely had time to cool and clump together when this galaxy was already blazing across the early universe. The source was surprisingly bright, which we wouldn't expect for such a distant galaxy. Astronomers admitted, in the infant universe, galaxies should be small, faint, and struggling to form their first stars. Instead, this ancient giant glows with an intensity that rivals much younger, more mature galaxies we observe in our cosmic neighborhood. The discovery forced scientists to question fundamental assumptions about galaxy formation. How could something so massive and luminous exist so early? What processes could have assembled so much matter and ignited so many stars in such a remarkably short time? Its age, size, and luminosity added to a growing body of evidence that current theories of early star and galaxy formation are incomplete. This single point of light in the darkness was telling us that the early universe was far more active and dynamic than our models had predicted. When astronomers split the light from Jade's GS Z14-0 into its component wavelengths, they uncovered a chemical signature that challenged everything we knew about the early universe. The galaxy was rich in nitrogen, unusually rich for such an ancient object. This discovery was like finding a sophisticated wine cellar in a house that was supposedly built yesterday. Nitrogen is not a primordial element that existed at the universe's birth. Instead, it must be forged inside stars and scattered into space when those stars die. Jade's analysis indicates that the brightness of the source, implied by the mere observation, is above what would be extrapolated from the measurements by the other Webb instruments, indicating the presence of strong ionized gas emission in the galaxy in the form of bright emission lines from hydrogen and oxygen. But nitrogen presented an even deeper puzzle. In the cosmic timeline, hydrogen and helium were the only elements present after the Big Bang. Every other element, from carbon to iron to nitrogen, had to be manufactured inside stellar furnaces over millions or billions of years. Stars live, burn through their nuclear fuel, and die, scattering these newly created elements into space, where they can be incorporated into the next generation of stars. This process takes time, lots of time. For a galaxy to be nitrogen-rich just 290 million years after the Big Bang, multiple generations of massive stars would have had to live entire life cycles, die in spectacular explosions, and seed the surrounding space with their chemical products. Imagine trying to find evidence of a great-grandparent's recipes in a cookbook written on the day a family first settled in a new country. The presence of complex, refined ingredients would suggest that many generations had already passed, even if the official records claimed otherwise. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that Jade's GS Z14-0 is forming stars in extremely dense environments. The connection between this ancient galaxy and the oldest stellar populations in our own cosmic neighborhood implied that rapid, intense star formation was occurring under conditions we had not fully understood. The nitrogen abundance pointed to what astronomers call chemical evolution happening at an accelerated pace. Normally, this process unfolds over billions of years as successive generations of stars gradually enrich their surroundings with heavier elements. But Jade's GS Z14-0 appeared to have compressed this timeline dramatically. That means galaxy evolution may have started much earlier than we thought. If massive stars were forming, living, and dying fast enough to produce significant nitrogen enrichment within the first few 100 million years of cosmic history, then the universe was far more active in its youth than our models predicted. The chemical fingerprints suggested that this galaxy was not a pristine, first-generation object, but rather the product of an already complex stellar ecosystem. Jade's GS Z14-0 was supposed to be an impossible outlier, a cosmic fluke that defied all expectations about the early universe. Instead, it opened the door to a much larger mystery. Given the relatively small region of the sky that we searched to find Jade's GS Z14-0, its discovery has profound implications for the predicted number of bright galaxies we see in the early universe. If such luminous objects could be found in a tiny patch of sky, how many more were waiting to be discovered across the vast cosmic landscape? Think of it like finding a bustling city while exploring what you thought was an empty wilderness. The discovery would immediately raise questions about how many other cities might exist in unexplored regions. Astronomers faced a similar situation as they realized that bright early galaxies might be far more common than anyone had imagined. Since its science observations began in July 2022, the JWST has discovered a series of increasingly distant ancient galaxies. Each new discovery pushed the boundaries further back in time, but also revealed that the early universe was populated with objects that should not have existed yet. The James Webb Space Telescope had only surveyed a minute fraction of the entire sky, yet it was consistently finding these bright, ancient galaxies. Statistical analysis suggested that there could be hundreds or even thousands of similar objects scattered across the cosmic deep field, each one representing a challenge to our understanding of early galaxy formation. Astronomers have used data from NASA's James Webb Space Telescope early release observations and discovered 87 galaxies that could be the earliest known galaxies in the universe. This growing population of ancient, bright objects was rewriting the cosmic census. Previous models had predicted that early galaxies would be small, faint, and rare. The universe should have been a relatively quiet place in its first few 100 million years, with star formation proceeding slowly and inefficiently. Instead, astronomers were finding evidence of vigorous stellar nurseries operating at full capacity when the cosmos was still in its infancy. These ancient, bright galaxies, sometimes called little red dots, are popping up across JWST's surveys. The nickname little red dots came from their appearance in early telescope images. But these objects were proving to be anything but insignificant. Each new discovery added weight to the growing realization that the early universe was far more active and structured than theoretical predictions had suggested. If bright galaxies were common in the cosmic dawn, it meant that the processes of star formation, element creation, and galactic assembly had proceeded much more rapidly than anyone had thought possible. It is likely that astronomers will find many such luminous galaxies, possibly at even earlier times, over the next decade with Webb. The James Webb Space Telescope was just beginning to explore the deepest reaches of space and time. Every major scientific theory rests on a foundation of carefully constructed models that predict how the universe should behave. When observations consistently contradict these predictions, scientists face a fundamental choice: modify the models or question whether something deeper is wrong with our understanding of reality itself. Current theories of early star and galaxy formation are incomplete. The discovery of Jade's GS Z14-0 and its bright companions was forcing astronomers to confront this uncomfortable truth. Decades of theoretical work had painted a picture of gradual cosmic evolution, but the universe was revealing a much more dramatic and rapid development. The spectroscopic confirmation of this source indicates the existence of many similar galaxies, particularly when considering the relatively small survey area of Jade's. This was not just one anomalous object that could be explained away as a special case. It was evidence of a systematic underestimation of how quickly the early universe could assemble complex structures. Consider a computer simulation designed to predict how a city will grow over time. If the simulation consistently predicts slow, gradual development, but satellite images reveal massive skyscrapers appearing in just the first few months, the underlying assumptions about construction rates and urban planning would need to be completely reconsidered. Cosmological models faced a similar crisis. The halo mass threshold required to yield a fixed co-moving abundance varies as the inverse sixth power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to host such massive galaxies should have been extremely rare at such early times. Dark matter halos provide the gravitational scaffolding upon which galaxies form. These invisible structures must grow to a sufficient size before they can begin efficiently converting gas into stars. According to standard models, the early universe should not have had enough time to grow halos massive enough to support the bright galaxies Webb was discovering. JADE's GS Z14-0 represents a fascinating, yet very challenging test case for the scenario that astronomers had developed to explain galaxy formation. The galaxy exhibited properties that stretched multiple theoretical frameworks to their breaking points. The crisis extended beyond just galaxy formation models. If the early universe was more structured and active than predicted, it might indicate problems with our understanding of dark matter, dark energy, or even the fundamental physics governing cosmic expansion. If galaxies like JADE's GS Z14-0 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? This question hung over the astronomical community like a storm cloud, suggesting that the discoveries might be symptoms of much deeper misunderstandings. Some theoretical physicists began to propose radical solutions. Perhaps the universe itself was not what it seemed to be. Perhaps the very stage upon which cosmic evolution played out was fundamentally different from what we had assumed. The discovery of JADE's GS Z14-0 marked the beginning of a cosmic treasure hunt that would reshape our understanding of the universe's earliest chapters. The astronomers agree that JWST's power has not yet reached its limits. None of them would be surprised if the telescope unveils a new redshift record within the year. The James Webb Space Telescope was operating like a time machine, systematically pushing back the boundaries of observable cosmic history. Astronomers realized they were standing at the edge of a new frontier. Every observation session brought the possibility of finding even more distant, even more impossible galaxies. This specific area JADES has been studying is pretty small. There are larger areas of the sky that have yet to be explored that maybe have even brighter and more distant galaxies. Picture archaeologists who had spent decades carefully excavating what they thought was a small, ancient settlement, only to discover that they were standing on the edge of a vast, buried metropolis. The scope of their task had suddenly expanded beyond anything they had imagined. JADE's GS C14-0 was the record holder at a redshift of 1432, but now another ancient bright galaxy has been found at a redshift of 14444, less than a year after the first discovery. An even more distant galaxy had been confirmed, pushing the cosmic frontier back by another 10 million years. This new record holder demonstrated that the pattern of unexpectedly bright early galaxies was not a fluke. This finding is surprising because astronomers expected to find very few galaxies at such a high redshift. Each new discovery reinforced the growing evidence that the early universe was far more active than anyone had predicted. The search was expanding beyond single telescope observations. Teams of astronomers around the world were coordinating efforts, sharing data, and developing new techniques to probe even deeper into cosmic time. Advanced computer algorithms were being trained to identify candidate distant galaxies in the vast data sets that Webb was collecting. Later this decade, the Nancy Grace Roman Space Telescope will join JWST in scanning the early universe. Roman will cover much larger areas of the sky with incredible detail. The Roman telescope would complement Webb's deep but narrow view with a wider survey capability, potentially discovering hundreds or thousands of ancient, bright galaxies. Together, these space telescopes would create the most comprehensive census of the early universe ever attempted. Every new galaxy discovered would add another piece to the puzzle of how cosmic structures formed and evolved during the universe's youth. But the implications extended far beyond simple discovery. Each ancient galaxy was a laboratory for testing our understanding of physics under extreme conditions. The densities, temperatures, and energy scales present during the formation of these early objects pushed matter to its limits. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away, while astronomers struggle to understand why ancient galaxies were brighter and more numerous than expected. A completely different mystery was emerging from the data. New research has uncovered an intriguing mystery that the majority of galaxies appear to be rotating in the same direction across vast regions of space. Galaxies seem to be spinning in a coordinated pattern, as if responding to some universal influence. In a truly random universe, galaxy rotations should be roughly evenly split between clockwise and counterclockwise directions when viewed from our perspective. Imagine throwing thousands of coins into the air and finding that 70% land heads up. Such a result would immediately suggest that either the coins are weighted or some external force is influencing their behavior. This is significant because in a truly random universe, galaxy rotations should be roughly evenly split between two directions. The discovery of a preferential rotation challenged one of the most fundamental assumptions in cosmology, that the universe is isotropic and homogeneous on large scales. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. The implications were staggering. If the universe has a preferred direction or axis, it would mean that space itself might have properties we had never suspected, like discovering that what appeared to be a perfectly smooth sphere actually has subtle ridges or patterns that influence everything that moves across its surface. Some researchers propose that this cosmic choreography might be evidence of rotation in the universe itself. If space-time possesses some form of overall angular momentum, it could impart a slight preference for rotational direction to the galaxies that form within it. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. The discovery was opening doors to exotic physics that operated on scales beyond anything we could directly test in laboratories. Alternative explanations were equally mind-bending. Perhaps the observed patterns were fossil remnants of processes that occurred during cosmic inflation, the theoretical period of rapid expansion that occurred in the universe's first fraction of a second. Or maybe they reflected the influence of dark matter structures that we could not directly observe. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Some physicists were beginning to wonder whether the coordinated galactic rotation might be evidence that our entire universe exists within such a boundary. Deep within the mathematics of general relativity lies a possibility so strange that most physicists had dismissed it as a mere curiosity. What if our entire universe exists inside a black hole? Some scientists interpreting the data have proposed something bold, that our entire universe might exist inside a black hole. This radical hypothesis, known as black hole cosmology, suggests that everything we observe, from distant galaxies to our own solar system, exists within the event horizon of a massive black hole in a larger parent universe. The theory emerged from attempts to reconcile the strange properties of the Big Bang with the physics of black holes. The standard model tells us that the universe began as a singularity, a point of infinite density, just like the center of a black hole. Both scenarios involve matter compressed to impossible densities under the influence of extreme gravitational fields. If our universe is actually the interior of a black hole that formed in a larger parent universe, it would mean that the Big Bang was not an explosion in empty space, but rather the moment matter collapsed into a black hole, creating a new universe inside. This would transform our understanding of cosmic origins from a mysterious beginning to a natural consequence of gravitational collapse in a higher dimensional reality. Consider the mathematical elegance of this possibility. Every property that makes our universe seem special, from its expansion rate to the values of the fundamental constants, could be natural consequences of existing within a black hole's interior. The apparent fine-tuning that allows complex structures like stars and galaxies to form might simply reflect the physics of black hole formation. Each and every black hole in our universe could be the doorway to another baby universe. This would create a fractal cosmos, where universes give birth to universes through the formation of black holes, each new universe potentially developing its own physics and evolutionary timeline. The theory offered elegant explanations for several cosmic puzzles. Black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. The connection between entropy and information could help resolve paradoxes about what happens to information that falls into black holes. Even more intriguingly, the coordinated rotation of galaxies that astronomers were discovering could be a natural consequence of existing within a rotating black hole. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward, potentially giving rise to a new universe inside. The mathematics suggested that quantum effects might prevent the formation of true singularities, causing collapsing matter to rebound and expand into new space-time regions. The scientists continued by adding that the rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. If our universe truly exists within a black hole, then every black hole we observe might be a doorway to an entirely new cosmos, complete with its own physics, planets, and perhaps even life. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing, self-replicating process. Instead of a single universe that appeared from nothing, we might inhabit one branch of an infinite cosmic tree, where each black hole represents both an ending and a beginning. Picture a vast cosmic ecosystem where universes reproduce through gravitational collapse. Just as biological organisms pass genetic information to their offspring, parent universes might transmit physical laws and constants to their cosmic children through the formation of black holes. This could explain why the fundamental forces in our universe seem precisely calibrated to allow complex structures to emerge. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. Universes with physics that promote stable star formation and complex chemistry would be more likely to produce the black holes necessary for cosmic reproduction. The implications were staggering. Every time a massive star collapses in our universe, it might be giving birth to a new cosmos containing billions of galaxies, each with their own planets and possibilities for life. The stellar death that marks an ending in our universe could simultaneously represent the Big Bang of another reality. This cosmic reproduction cycle would operate on timescales that dwarf biological evolution. While life on Earth has evolved over billions of years, cosmic evolution would unfold over trillions of generations of universe formation and development. Each new universe would be a cosmic experiment, testing slightly different combinations of physical laws and constants. The black hole universe theory also offered a potential resolution to the horizon problem in cosmology. Our universe appears remarkably uniform in temperature and structure across regions that should never have been in causal contact. If our cosmos began as the interior of a pre-existing black hole, this uniformity could be inherited from the parent universe's properties. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. Quantum mechanical effects operating at the smallest scales might create the cosmic bounce that transforms gravitational collapse into universal expansion. The mathematics of this process remain challenging, but the conceptual framework was elegant. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. Our Big Bang would be just one moment in an endless cycle of cosmic death and rebirth. Standing at the edge of cosmic understanding, astronomers find themselves equipped with tools powerful enough to peer back to the very dawn of time, yet humble enough to realize how much remains unknown. If it survives repeated cancellation threats, the Roman Space Telescope should reveal hundreds more of these types of galaxies. The future of cosmic archaeology depends not just on technological advancement, but on humanity's commitment to exploring the deepest questions about our existence. The Nancy Grace Roman Space Telescope, with its wide field capabilities, will complement the James Webb Space Telescope's deep but narrow view. Together, these instruments will conduct the most comprehensive survey of the early universe ever attempted. Where Webb finds individual ancient galaxies with exquisite detail, Roman will map their distribution across vast regions of space. A larger data set is always desirable and would help solidify some of these findings, or maybe introduce new mysteries. Science advances through the accumulation of evidence, but it also thrives on the discovery of new puzzles that challenge existing theories. The statistical power of hundreds or thousands of early galaxy observations will allow astronomers to test whether the current discoveries represent genuine departures from theoretical predictions or simply the extreme tail of expected distributions. More data will either confirm that galaxy formation proceeded much more rapidly than predicted or reveal new physics operating in the early universe. But the implications extend far beyond astronomy. The universe is turning out to be far stranger than we ever imagined. And the uneven galactic rotations will likely prompt astrophysicists to reassess certain aspects of our understanding of the universe. Each new discovery forces us to question assumptions we thought were rock solid. The coordinated rotation of galaxies across cosmic distances might indeed point to our universe existing within a larger structure. Or it might reveal new physics operating on scales we can barely comprehend. Either possibility would fundamentally change how we understand our place in the cosmic hierarchy. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. Sometimes, revolutionary discoveries turn out to have more mundane explanations, but the process of investigating them always advances our knowledge. Future observations will probe even deeper into cosmic time, perhaps eventually reaching the era when the very first stars ignited in the primordial darkness. These population 3 stars, composed only of hydrogen and helium, would have been massive giants that lived brief but spectacular lives, seeding space with the heavier elements necessary for planets and life. Scientists using Webb to study GNZ11 have also uncovered some tantalizing evidence for the existence of population 3 stars nestled in the outskirts of this remote galaxy. The discovery of these primordial stars would complete our picture of how the universe transitioned from simplicity to complexity, supermassive black holes, with masses millions or billions of times greater than our sun, typically power the brightest objects in the universe. These cosmic engines devour gas and dust, heating material to millions of degrees and launching it outward in brilliant jets of plasma. When astronomers spot an exceptionally bright galaxy, they usually expect to find one of these giants lurking at its center. Jade's GS Z14-0 defied this expectation completely. From the images, the source is found to be over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from emission near a growing supermassive black hole. The galaxy's brightness was not the product of a feeding black hole, but rather an explosive nursery of newborn stars. This absence created a cosmic puzzle. Most galaxies that shine this brightly rely on the intense radiation generated by matter spiraling into a supermassive black hole. These black holes act like cosmic lighthouses, often outshining all the stars in their host galaxies combined. But Jade's GS Z14-0 was generating its tremendous luminosity through pure stellar formation. Think of it like discovering a medieval village that somehow produces the same amount of light as a modern city, but without any electrical power. The village would need to have an impossibly large number of torches and fires burning simultaneously. Similarly, this ancient galaxy needed to be forming stars at a rate that seemed almost impossible for its era. The galaxy has a star formation rate, averaged over the last 10 million years, of approximately 22 solar masses per year. That means every single year, this galaxy converts material equivalent to 22 suns into newborn stars. For such a young cosmic age, this rate represents a stellar baby boom of unprecedented proportions. The implications stretch far beyond this single galaxy. Supermassive black holes are thought to play crucial roles in regulating star formation throughout their host galaxies. They can both trigger star birth by compressing gas clouds and halt it by blowing material away with powerful winds. Without a central black hole, how is this galaxy managing to form stars so efficiently? Even more puzzling, most theoretical models suggest that supermassive black holes and their host galaxies grow together over cosmic time. The absence of a detectable black hole in such a massive early galaxy challenged this fundamental relationship. All of these observations, together, tell us that Jade's GS Z14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe. It was operating by rules we had not yet discovered, hidden in the outskirts of ancient galaxies. Astronomers are searching for the universe's very first stars. These elusive objects, known as Population 3 stars, would have been the cosmic pioneers that brought light to a universe filled only with hydrogen and helium. No definitive detection of such stars has ever been made, but scientists know they must exist. Now, with Webb, their discovery seems closer than ever before. Scientists using Webb to study another ancient galaxy have also uncovered some tantalizing evidence for the existence of Population 3 stars nestled in the outskirts of this remote galaxy. These primordial giants would have been fundamentally different from any star we observe today, composed entirely of the simplest elements forged during the Big Bang. Picture the universe in its first 100 million years as a vast, dark ocean punctuated by islands of light. Population 3 stars would have been these first beacons, massive beyond anything we see in the modern cosmos. Without heavier elements to help them radiate energy efficiently, these stars would have grown to enormous sizes, perhaps 50 to 100 times more massive than our sun. Their lives would have been spectacular, but brief. burning through their nuclear fuel in just a few million years. These stellar giants would have ended their existence in catastrophic explosions that scattered the first heavy elements across space. Carbon, oxygen, nitrogen, and iron, forged in their nuclear furnaces, would become the building blocks for the next generation of stars, and eventually for planets and life itself. The search for population 3 stars represents one of astronomy's greatest challenges. These objects existed so long ago that their light has been traveling for over 13 billion years to reach us. Even the most powerful telescopes struggle to detect individual stars at such extreme distances. But Webb's infrared vision offers new hope. When population 3 stars exploded as supernovas, they would have created distinctive signatures in the surrounding gas clouds. These fingerprints might still be visible today, encoded in the light from galaxies that formed in regions enriched by the first stellar explosions. Looking deeply into space and time, 2 teams using NASA's James Webb Space Telescope have studied the exceptionally luminous galaxy, which existed when our 13.8 billion-year-old universe was only about 430 million years old. This galaxy shows chemical patterns that might reflect the influence of population 3 stellar explosions. A second team used Webb's near-infrared spectrograph to find a gaseous clump of helium in the halo surrounding this ancient galaxy. Pure helium clouds are exactly what astronomers would expect to find if population 3 stars had recently exploded nearby, seeding space with their nuclear products while leaving behind pockets of pristine, primordial gas. The discovery of these cosmic fossils would complete our understanding of how the universe transitioned from darkness to light. Population 3 stars were the match that lit the cosmic candle, beginning the long chain of stellar evolution that eventually led to our solar system. Each ancient galaxy discovered by Webb brings us closer to finding direct evidence of these first stars. Every element heavier than hydrogen and helium tells a tale of stellar alchemy, of massive stars that lived, died, and scattered their nuclear products across space. This cosmic recycling program transformed a universe of simple gases into one capable of supporting rocky planets, organic molecules, and eventually, life itself. When astronomers examine the light from Jade's GS Z14-0 and other ancient galaxies, they are reading the chemical diary of the early universe. Each emission line in their spectra represents a different element, and the relative intensities reveal how much of each element was present when that light was emitted. The nitrogen abundance in these early galaxies presents a cosmic puzzle that challenges our understanding of stellar evolution timescales. Nitrogen is primarily produced inside intermediate mass stars through a complex series of nuclear reactions that typically require hundreds of millions of years to complete. Yet these galaxies existed when the universe was barely 300 million years old. For them to show significant nitrogen enrichment, stellar evolution must have proceeded much more rapidly than our current models predict, or entirely different physical processes were at work in the early cosmic environment. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that similar physical conditions existed both in the early universe and in the dense environments where globular clusters form. The connection implies that we might be observing universal principles of star formation operating under extreme conditions. The implications extend far beyond individual galaxies. If chemical evolution proceeded rapidly throughout the early universe, it would mean that the building blocks for complex chemistry became available much sooner than previously thought. Rocky planets could have formed earlier, organic molecules could have emerged sooner, and the window for life to develop would have opened billions of years ahead of schedule. Consider the profound philosophical implications. If the universe became chemically mature much earlier than we believed, then Earth-like worlds and and potentially life itself, might have had far more time to develop and evolve. We might be late arrivals to a cosmic party that has been ongoing for much longer than anyone imagined. The rapid chemical enrichment also suggests that feedback processes between stars and their surrounding gas operated differently in the early universe. Stellar winds and supernova explosions would have mixed freshly synthesized elements through space more efficiently, accelerating the pace of cosmic evolution. Furthermore, as noticed by recent studies, these morphological differences are reflected in chemical abundance patterns, signaling a deeper connection between galaxy structure and evolutionary pathways. Compact galaxies tend to show different chemical signatures than extended ones, suggesting that physical size and chemical evolution are intimately linked. The universe was conducting chemistry experiments on a cosmic scale, testing different combinations of stellar masses, formation rates, and environmental conditions. Each ancient galaxy represents a different outcome of these experiments. Invisible scaffolding shapes everything we see in the universe. Yet the discovery of impossibly early, massive galaxies suggests this cosmic architecture might work differently than we thought. Dark matter. The mysterious substance that comprises over 80% of all matter in the universe provides the gravitational framework upon which galaxies form. According to our best theories, ordinary matter falls into dark matter halos, accumulating until it reaches the critical density needed to ignite star formation. This process should take time, lots of time. Dark matter halos must grow through countless mergers and accretion events before they become massive enough to host the bright galaxies that Webb is discovering. The standard model of cosmic structure formation predicts that truly massive halos should have been extremely rare in the first few 100 million years after the Big Bang. Yet JADE's GS-Z14-0 and its companions exist in apparent defiance of these predictions. The halo mass threshold required to yield a fixed come-moving abundance varies as the inverse sixth power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to support such massive early galaxies should have been vanishingly rare. Think of it like finding skyscrapers in a city that was supposedly founded just last week. The construction requires not just time, but also the development of sophisticated infrastructure, supply chains, and engineering expertise. Similarly, massive galaxies require mature dark matter halos that should not have existed so early in cosmic history. From a theoretical simulation, we estimate that the probability of finding halos massive enough to host these bright early galaxies was incredibly low. The simulations suggest we should have found perhaps one such object in the entire observable universe, not dozens scattered across Webb's relatively small survey areas. This discrepancy points to several possible explanations, each with profound implications for our understanding of cosmic evolution. Perhaps dark matter behaves differently than we assumed, interacting with itself or with ordinary matter in ways that accelerate halo formation. Or maybe the relationship between halo mass and galaxy brightness is not what our models predict. Alternative theories propose that dark matter might have additional properties that become important in the extreme conditions of the early universe. Self-interacting dark matter, for instance, could undergo rapid collapse and rebound cycles that efficiently concentrate mass into the cores of halos. Another possibility is that early star formation was far more efficient than current models suggest. If the first stars could form with much less dark matter support than is required today, then bright galaxies could appear in smaller halos that were more common in the early universe. The puzzle deepens when we consider that these early galaxies show evidence of multiple generations of stellar evolution. Not only did they form earlier than expected, but they also evolved faster, cycling through stellar birth and death at an accelerated pace that compressed billions of years of evolution into a few hundred million. In the cosmic dance between stars and galaxies, energy flows in both directions, creating feedback loops that should regulate and limit how quickly galaxies can grow. When massive stars explode as supernovas, they release tremendous amounts of energy that heats the surrounding gas and blows it away from the galaxy. This process, known as stellar feedback, acts like a cosmic thermostat, preventing galaxies from forming stars too quickly and burning through their gas reserves. Similarly, when gas falls into supermassive black holes, it generates powerful winds and jets that can clear entire galaxies of star-forming material. These feedback mechanisms are thought to be essential for explaining why galaxies do not convert all of their available gas into stars within the first few million years of their existence. Yet the ancient galaxies discovered by Webb seem to have bypassed these cosmic speed limits entirely. JADE's GS-Z14-0 shows evidence of vigorous star formation occurring at rates that should have triggered feedback processes strong enough to shut down further stellar birth. The galaxy exhibits properties that stretched multiple theoretical frameworks to their breaking points. Its high star formation rate, combined with its large stellar mass, suggests that feedback mechanisms were either much weaker in the early universe, or that these galaxies had access to continuous supplies of fresh gas to fuel their incredible growth. Consider the energy budget involved. Every time a massive star explodes, it releases energy equivalent to our sun's entire lifetime output in just a few seconds. Multiple supernovas exploding within a small galaxy should create a devastating storm of hot gas and radiation that prevents new stars from forming for millions of years. But these early galaxies appear to have weathered such cosmic storms without interruption. Some theoretical models suggest that the dense environment of the early universe might have allowed galaxies to retain their gas despite energetic feedback processes. The rapid chemical enrichment observed in these galaxies provides additional evidence that stellar feedback was not effectively removing freshly synthesized elements from star-forming regions. Instead of being blown away by stellar winds, heavy elements were apparently retained and incorporated into subsequent generations of stars. This retention of metals and gas implies that early galaxies were more efficient at converting raw materials into stars than their modern counterparts. The physics of star formation itself might have operated differently when the universe was young and dense. Another possibility is that these galaxies were fed by continuous streams of pristine gas falling in from the cosmic web. If the accretion rate was high enough, it could overwhelm the feedback processes and maintain a steady rate of star formation despite ongoing stellar explosions. The crisis in feedback theory extends beyond individual galaxies to cosmic evolution as a whole. If early galaxies could grow without the regulatory mechanisms that govern modern star formation, then the entire timeline of cosmic structure formation might need to be reconsidered. Stretching across billions of light years, an invisible network of dark matter filaments connects galaxies throughout the universe, forming the cosmic web that defines large-scale structure. This vast scaffolding channels gas and dark matter along preferred pathways, feeding material to galaxies at the intersections where filaments meet. The cosmic web grows gradually over time, with the most massive structures forming at the nodes where multiple filaments converge. According to standard models, the early universe should have had only the most rudimentary web structure. The first few hundred million years after the Big Bang would have been dominated by small-scale fluctuations, with large-scale organization developing slowly as gravity amplified the tiny density variations left over from cosmic inflation. Yet the discovery of numerous bright galaxies at extreme distances suggests that the cosmic web was already remarkably well developed when the universe was barely 300 million years old. These galaxies appear to be located at the major intersections of dark matter filaments, implying that large-scale structure formation proceeded much more rapidly than predicted. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. Picture the cosmic web as a three-dimensional spiderweb spanning the entire observable universe. In the standard picture, this web should have been sparse and incomplete during the cosmic dawn, with only small sections connected to each other. Instead, observations suggest that the major highways of the cosmic web were already in place, efficiently channeling material to the galaxy formation sites. The implications are staggering. If large-scale structure formation proceeded much faster than our models predict, it might indicate that dark matter and dark energy behave differently than we assume, or that additional physical processes were at work during the universe's earliest epochs. Alternative explanations invoke exotic physics operating during cosmic inflation. Perhaps the quantum fluctuations that seeded cosmic structure were not as random as we believed, but instead carried subtle patterns that accelerated the formation of these large-scale networks. Another possibility is that the cosmic web itself influences galaxy formation in ways we have not fully understood. Rather than simply providing the scaffolding for galaxy assembly, the web might actively channel energy and matter in patterns that enhance the efficiency of star formation. The discovery of bright early galaxies at what appear to be the nodes of the cosmic web suggests that the relationship between large-scale structure and galaxy formation was already well established when the universe was remarkably young. One of cosmology's most enduring puzzles concerns how the universe achieved such remarkable uniformity across regions that should never have been in causal contact. The cosmic microwave background radiation, the afterglow of the Big Bang, shows the same temperature to within 1 part in 100,000 across the entire sky. This uniformity extends to regions separated by distances so vast that light has not had time to travel between them since the universe began. How can regions that have never exchanged information display such identical properties? This horizon problem has plagued cosmologists for decades, leading to the development of the cosmic inflation theory as a proposed solution. Inflation suggests that the universe underwent a brief period of exponential expansion in its first fraction of a second, stretching tiny, causally connected regions to cosmic scales. This would explain how distant parts of the universe share the same temperature and other properties. But the discovery of impossibly bright and massive galaxies in the cosmic dawn adds a new dimension to the horizon problem. These objects appear to have formed too quickly and grown too large for the available time, suggesting that the early universe was more interconnected and organized than the standard model allows. If our cosmos began as the interior of a pre-existing black hole, this uniformity could be inherited from the parent universe's properties. The horizon problem would dissolve because our universe would have inherited its uniform properties from a larger, already connected system. This black hole cosmology offers an elegant resolution to several cosmic puzzles simultaneously. The Big Bang would not represent the beginning of time, but rather a phase transition from gravitational collapse to expansion, carrying forward the organized properties of the parent universe. Consider the implications for early galaxy formation. If our universe inherited large-scale structure from its parent, then the cosmic web could have been partially assembled from the very beginning. This would explain how massive galaxies could form so quickly, in apparent violation of the bottom-up structure formation models. The coordinated rotation of galaxies across cosmic distances might be another inherited property, reflecting an angular momentum present in the parent universe at the time of black hole formation. Instead of emerging randomly from quantum fluctuations, large-scale patterns could be the fossil remnants of the parent cosmos. Recent observations of cosmic anisotropy, where galaxies show preferred orientations across vast regions of space, support the idea that the universe possesses large-scale, coherent properties that extend beyond what inflation alone can explain. If these patterns represent inherited characteristics from a parent universe, then many aspects of cosmic evolution that seem fine-tuned or improbable might actually be the natural consequences of our universe's nested origin within a larger cosmological system. The horizon problem, long considered evidence for exotic physics during cosmic inflation, might instead point toward an even more exotic possibility that our universe is one of countless cosmic offspring, each inheriting its properties from its parent through the formation of black holes. The fundamental constants of nature appear to be precisely calibrated to allow the existence of stars, planets, and life, a phenomenon that has puzzled scientists for generations. Change the strength of the strong nuclear force by just a few %, and atomic nuclei would not be stable. Alter the ratio of the electron and proton masses slightly, and chemistry as we know it would be impossible. Adjust the cosmological constant that drives cosmic expansion, and galaxies might never form or might fly apart before stars can ignite. This apparent fine-tuning has led to intense debates about why our universe seems so perfectly suited for complexity in life. Some invoke the anthropic principle, arguing that we observe these values simply because we exist to observe them. Others propose the existence of multiple universes with different physical laws, making our life-friendly cosmos just one possibility among countless others. But the black hole universe theory offers a radically different perspective on this fine-tuning. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. Imagine cosmic evolution as a vast reproductive process, where universes that develop stable physics are more likely to create the black holes necessary for producing offspring universes. Over countless generations of cosmic reproduction, natural selection would favor physical constants that promote complexity, structure formation, and long-term stability. Universes with physics that promote stable star formation and complex chemistry would be more likely to produce the black holes necessary for cosmic reproduction. Those with constants that prevent galaxy formation or cause rapid collapse would be evolutionary dead ends, unable to propagate their physical laws to future generations. This cosmic natural selection would explain not only why our universe supports complexity, but also why the early galaxies discovered by Webb show such sophisticated chemical evolution. If our cosmos inherited its physics from a long lineage of successful parent universes, then rapid structure formation and efficient star formation might be deeply embedded characteristics. The fine-tuning paradox dissolves when viewed through this reproductive lens. Rather than being improbably perfect by chance or by design, our universe's properties would be the product of eons of cosmic evolution, refined through countless cycles of birth, development, and reproduction. Each generation of universes would inherit the successful physical constants of their parents, while potentially introducing small variations through the quantum mechanical processes operating during black hole formation. Over cosmic time, This would lead to the gradual optimization of physical laws for promoting complexity and longevity. The apparent youth and sophistication of the early galaxies fits naturally into this framework. If our universe descended from a long line of successful parent cosmos, it would have inherited not just fine-tuned constants, but also the capacity for rapid and efficient structure formation. Deep within the mathematics of black hole physics lies one of the most profound puzzles in modern science. What happens to information when it falls beyond the event horizon? According to quantum mechanics, information cannot be truly destroyed. Every particle, every quantum state, every bit of data about the physical world must be preserved in some form, even if it becomes impossible to access or decode. Yet black holes appear to violate this fundamental principle. When matter falls into a black hole, it seems to vanish from our universe completely, taking with it all the information about its quantum states, its history, and its properties. Stephen Hawking showed that black holes eventually evaporate through thermal radiation. But this radiation appears to carry no information about what fell in, creating an apparent paradox. But if our universe exists within a black hole, this paradox takes on a new and profound significance. Black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Every star, planet, atom, and quantum state in our cosmos would contribute to the total information content stored within the black hole that contains us. This connection offers a potential resolution to the information paradox. Rather than being destroyed, the information that falls into black holes might give birth to new universes, each one encoding and preserving the quantum states that entered the black hole. The information would not be lost, but transformed into the initial conditions for a new cosmic system. Consider the staggering implications. Every black hole in our universe might contain not just compressed matter, but entire cosmological systems with their own galaxies, stars, and potentially life. The black holes we observe through our telescopes could be windows into countless other realities, each one as vast and complex as our own. This nested structure would create a cosmic library of unimaginable scale, where information is preserved across multiple levels of reality. The quantum states that fell into ancient black holes in parent universes might be encoded in the fundamental constants and initial conditions of our cosmos. The rapid formation of complex galaxies in our early universe might reflect information inherited from previous cosmic generations, rather than starting from simple initial conditions. Our universe could have begun with sophisticated organizational templates encoded in its basic structure. Each ancient galaxy discovered by Webb would represent not just early star formation, but the expression of cosmic information patterns inherited from parent universes. The chemical complexity, the structural organization, and the rapid evolution of these galaxies might be the manifestations of information processing operating on cosmological scales. If black holes preserve and transform information rather than destroying it, then every supermassive black hole in our universe serves as both an ending and a beginning. A cosmic recycling center where the information content of one reality becomes the foundation for new cosmic systems. At the heart of every black hole lies a mystery that challenges our understanding of space, time, and the fundamental nature of reality itself. Classical physics predicts that matter falling into a black hole will collapse into a singularity, a point of infinite density where the laws of physics break down completely. But quantum mechanics suggests a different fate, one that could transform cosmic death into cosmic birth. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. Instead of crushing matter into mathematical points, quantum effects might create a cosmic bounce that rebounds outward, giving birth to new, expanding universes. This quantum bounce mechanism operates through the inherent uncertainty principles that govern matter at the smallest scales. When particles are compressed to densities approaching the Planck scale, quantum fluctuations become so intense that they generate an outward pressure strong enough to halt and reverse the gravitational collapse. Picture a cosmic trampoline stretched to its absolute limit. Just as a ball dropped onto a trampoline will bounce back upward if the elastic force exceeds the downward momentum, matter collapsing into a black hole might rebound when quantum pressure overcomes the gravitational attraction. The scientists continued by adding that the rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. This mechanism would explain many of the puzzling features of our universe's early evolution. The rapid formation of large-scale structures, the sophisticated chemistry of early galaxies, and the apparent fine-tuning of physical constants could all be inherited characteristics from the parent universe, transmitted through the quantum bounce process. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce where the core rebounds and expands outward, potentially giving rise to a new universe inside. The process would conserve information while transforming it into new forms of cosmic organization. The quantum bounce would not be instantaneous, but might occur over cosmic timescales from the perspective of the new universe. What appears as the Big Bang and subsequent cosmic evolution to us might represent the gradual expansion following the quantum rebound of matter in a parent universe's black hole. This process could operate recursively, with each new universe capable of forming its own black holes and spawning additional cosmic offspring. The result would be an infinite, fractal structure where universes give birth to universes through cycles of collapse and quantum rebound. The early galaxies discovered by Webb might be direct evidence of this process at work. Their rapid formation and sophisticated properties could reflect the efficient transfer of organizational information from a parent to an offspring universe through the quantum bounce mechanism. Each black hole in our cosmos would be both a cosmic endpoint and a cosmic beginning, transforming the matter and information of our universe into the seeds of new realities through the mysterious quantum processes that operate at the intersection of gravity and quantum mechanics. If our universe exists within a black hole, then we must confront the possibility that reality is organized as an infinite hierarchy of nested cosmic systems. Every black hole we observe, from stellar mass objects to the supermassive giants at galaxy centers, could contain entire universes with their own galaxies, stars, planets, and potentially life. This would create a cosmic matryoshka doll of staggering proportions, where each level of reality contains countless sub-levels, extending downward into infinity. Consider the scale relationships involved. A supermassive black hole in our universe might contain a cosmos with billions of galaxies, each hosting billions of stars. Some of those stars would form their own black holes, creating additional layers of nested reality. The recursive structure would continue indefinitely, with no fundamental limit to the depth of cosmic organization. From our perspective, we occupy one specific level in this hierarchy. We can observe black holes that might contain entire universes, but we cannot directly communicate with or influence those nested realities. Similarly, if our universe exists within a black hole in a parent cosmos, the inhabitants of that larger reality would be unable to directly observe or interact with us. This cosmic hierarchy would operate according to fundamental principles of information, preservation, and transformation. Each level would inherit properties from its parent, while developing its own unique characteristics through the processes of cosmic evolution. The rapid formation of complex structures in our early universe might reflect our position in this hierarchy. If our cosmos inherited organizational templates from a parent universe, then sophisticated galaxy formation could proceed much more efficiently than models based on starting from simple initial conditions predict. Each new level of the hierarchy would represent a different scale of cosmic organization. Just as atoms combine to form molecules, molecules form cells, and cells form organisms. Universes might combine to form larger-scale structures that we cannot currently imagine or detect. The hierarchy might extend upward as well as downward. Our parent universe could itself be nested within an even larger cosmic system, which in turn exists within another level of reality. The ultimate structure could be infinite in both directions, with no fundamental top or bottom to the cosmic organization. This perspective transforms our understanding of cosmic significance. Rather than being isolated observers in a unique universe, we would be participants in an infinite network of cosmic consciousness, each level contributing to the overall complexity and information content of the universal hierarchy. The black holes we study with our telescopes would not be cosmic monsters devouring matter and energy, but cosmic wombs, nurturing new universes through their mysterious interiors. Each would represent a portal between different levels of reality, facilitating the flow of information and organization across cosmic scales. If every black hole contains a universe potentially harboring billions of intelligent civilizations, then consciousness might be far more abundant and significant in the cosmic scheme than we ever imagined. Rather than being rare accidents in an otherwise lifeless cosmos, thinking beings could be fundamental components of universal organization. Consider the information processing requirements of a nested universe system. Each level of the hierarchy would need to maintain, organize, and transform vast amounts of information as it inherits properties from parent universes and potentially gives birth to offspring cosmos. Consciousness might serve as the universe's method for processing and organizing this cosmic information. Intelligent civilizations could function as the universe's neurons, collecting data about their local cosmic environment, processing it through scientific observation and theoretical understanding, and potentially transmitting that information to other levels of the hierarchy through mechanisms we do not yet comprehend. The rapid development of complex structures in our early universe might reflect not just inherited physical organization, but inherited patterns of information processing. If parent universes develop sophisticated mechanisms for organizing matter and energy through the activities of conscious beings, these templates could be passed down to offspring cosmos. Each ancient galaxy discovered by Webb might represent not just stellar formation, but the emergence of information processing networks that will eventually give rise to consciousness and intelligence. The chemical complexity observed in these early systems provides the necessary building blocks for organic chemistry and, potentially, life. This perspective suggests that consciousness and cosmic evolution are intimately connected, rather than being separate phenomena. The development of intelligence and the organization of cosmic structure might be different aspects of the same fundamental process of universal information integration. The coordinated rotation of galaxies across vast distances might reflect large-scale information processing operating on cosmic scales. Just as neural networks in biological brains show coordinated activity patterns, galaxy networks might display similar coherence as they participate in universe-scale computational processes. If our universe exists within a black hole in a parent cosmos, then our scientific observations and theoretical understanding might be contributing to the information processing occurring at that higher level of organization. Our attempts to understand cosmic evolution could be part of the parent universe's effort to understand itself. Quantum mechanics tells us that the act of observation fundamentally changes the systems being observed, collapsing probability waves into definite states and determining the outcome of quantum measurements. But what if this observer effect operates on cosmic scales, with consciousness playing a fundamental role in determining the large-scale structure and evolution of the universe itself? If our universe exists within an infinite hierarchy of nested black hole cosmos, then conscious observers at each level might be actively participating in the creation and maintenance of reality at their scale. Our scientific observations and measurements could be helping to determine not just what we discover about the universe, but what properties the universe actually possesses. The anthropic principle suggests that we observe the universe to have properties compatible with our existence simply because we exist to observe them. But in a nested cosmic hierarchy, this relationship might be far more active and dynamic than previously imagined. Consider the implications for the ancient galaxies discovered by Webb. These objects formed when the universe was young and its properties were still stabilizing. The act of observing them now, billions of years after their formation, might be retroactively influencing their properties through quantum mechanical connections that operate across cosmic time. This would create a cosmic bootstrap paradox, where the universe develops properties that ensure the eventual emergence of observers capable of studying its early evolution. The observer effect would operate across space and time, creating self-consistent cosmic histories that support the development of consciousness. The rapid formation of complex structures in the early universe might reflect this observer-driven cosmic evolution. If consciousness at various levels of the cosmic hierarchy is actively participating in cosmic organization, then galaxy formation could proceed much more efficiently than purely physical processes would allow. Quantum entanglement might provide the mechanism for this cosmic scale observer effect. If particles and systems throughout the universe remain quantum mechanically connected across vast distances and timescales, then conscious observations anywhere in the cosmos could influence conditions everywhere else. The coordinated rotation of galaxies across cosmic distances might be evidence of this quantum entanglement operating on large scales. Rather than being independent systems, galaxies could be components of a vast quantum network, where measurement and observation at one location instantly affects conditions throughout the entire system. This perspective transforms scientific observation from passive data collection into active participation in cosmic creation. Every measurement we make, every theory we develop, every discovery we announce could be contributing to the ongoing process of universal self-organization. The nested universe hierarchy would amplify this effect across multiple levels of reality. Conscious observers in parent universes might be influencing the conditions in our cosmos, while our observations might be affecting the universes nested within the black holes in our local cosmic neighborhood. If our universe truly exists within a black hole in a larger parent cosmos, it raises a fascinating question about communication and information transfer between the different levels of the cosmic hierarchy. According to general relativity, nothing can escape from within a black hole's event horizon, including light, matter, and information. This would seem to make communication between nested universes impossible, trapping each cosmic level in complete isolation from its parents and its offspring. Yet the existence of organized structures and apparent fine-tuning in our universe suggests that information has somehow been transmitted from parent systems. The rapid formation of complex galaxies, the sophisticated chemistry of early star formation, And the coordinated patterns observed on cosmic scales all point to inherited organizational templates. The solution to this communication paradox might lie in the quantum mechanical nature of black hole formation and evolution. When a black hole forms through gravitational collapse, it does not instantly cut off all connection to the outside universe. Instead, the process of horizon formation and information encoding might allow for sophisticated transfer mechanisms operating through quantum entanglement. Hawking radiation provides one potential communication channel. As black holes slowly evaporate, they emit particles that might carry encoded information about the internal universe. From the perspective of the parent cosmos, this radiation could provide a slow but steady stream of data about the conditions within the nested universe. From our perspective within a black hole universe, we might be able to influence this communication channel through our collective activities as conscious observers. The development of advanced civilizations, the creation of complex technologies, and even the pursuit of scientific understanding might all contribute to information patterns that eventually influence the Hawking radiation emitted by our containing black hole. Consider the timescales involved. While communication through Hawking radiation would be extraordinarily slow from our internal perspective, it might operate efficiently from the viewpoint of the parent universe, where our entire cosmic history unfolds in a much shorter time frame due to relativistic effects. The coordinated galactic rotations observed across our universe might represent a form of cosmic scale information encoding. If consciousness throughout our cosmos collectively organizes matter and energy in specific patterns, these patterns could be transmitted to the parent universe through quantum mechanical channels we do not yet understand. Another possibility involves the moment of black hole formation itself. The initial conditions that gave birth to our universe might have been encoded with sophisticated information templates from the parent cosmos. Rather than requiring ongoing communication, all the necessary organizational information could have been transmitted during the quantum bounce that created our expanding space-time. The rapid evolution of the early galaxies discovered by Webb might be direct evidence of this encoded information being expressed. As our universe expanded and cooled, the inherited organizational templates would begin to manifest as complex structures, forming much more quickly than purely random processes would allow. This suggests that while we cannot send messages back to our parent universe in any conventional sense, our collective development as a cosmic system might be generating information patterns that influence the properties of our containing black hole. In essence, our universe's evolution could be a form of slow, cosmic scale communication. As we stand at the threshold of discoveries that could revolutionize our understanding of reality itself, we must confront questions that stretch the boundaries of science, philosophy, and human comprehension. If our universe exists within an infinite hierarchy of nested black hole cosmos, what does this mean for the concepts of beginning and ending, of uniqueness and significance, of isolation and connection? The very foundations of how we think about existence might need to be rebuilt from the ground up. The discovery of impossibly bright and sophisticated galaxies in our cosmic dawn forces us to question whether we have fundamentally misunderstood the nature of time, causality, and cosmic evolution. Perhaps what we interpret as rapid galaxy formation is actually the expression of organizational patterns that transcend our local space-time. Inherited from parent universes through quantum mechanical processes we can barely imagine, the question echoes across cosmic scales. From individual human curiosity to universal self-inquiry. If consciousness plays a fundamental role in cosmic organization, then our wondering about these mysteries might be contributing to the universe's own effort to understand its place in the larger hierarchy of reality. The The ancient galaxies that prompted this investigation might be more than just astronomical objects. They could be cosmic fossils, preserving information about our universe's ancestry. Quantum archaeological artifacts that encode the history of how our reality inherited its properties from parent systems. Each discovery pushes us to confront the possibility that everything we thought we knew about cosmic uniqueness might be wrong. Rather than inhabiting a singular universe that began with the Big Bang and will end with heat death or collapse, we might be temporary participants in an infinite cycle of cosmic reproduction and evolution. The implications for human meaning and significance are profound. If our universe is one of countless nested realities, does this diminish our importance or enhance it? Are we cosmic accidents or essential components of universal self-organization? Do our lives and achievements matter only locally? Or do they contribute to information processing occurring on scales we cannot comprehend? The coordinated rotation of galaxies across cosmic distances might be evidence that we are already participating in forms of cosmic consciousness that operate beyond individual awareness. Our scientific discoveries, our technological achievements, and even our philosophical questioning might be contributing to patterns of cosmic organization that span multiple levels of the universal hierarchy. As astronomers continue to peer deeper into space and time with increasingly powerful instruments, they are simultaneously looking deeper into questions about the nature of reality itself. Each new ancient galaxy discovered represents not just another data point, but another piece of evidence that the universe is far stranger and more interconnected than our theories had suggested. The James Webb Space Telescope and its successors might be doing more than just studying distant objects. They might be facilitating communication between the different levels of cosmic organization, helping our universe to understand its place in the infinite hierarchy of nested realities. The ultimate questions are not just about what we will discover, but about how those discoveries will change our understanding of what it means to exist in a universe that might be far more alive, connected, and purposeful than we ever dared to imagine. Looking forward to the next decade of cosmic discovery, we find ourselves standing at the edge of what might be the greatest revolution in human understanding since we first realized that the Earth orbits the Sun. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will survey vast areas of the sky with unprecedented depth and precision, where Webb has opened windows into individual ancient galaxies. Roman will map the cosmic landscape on scales that could reveal the true extent of early universe complexity. Together, these space-based observatories will create the most comprehensive census of the cosmic dawn ever attempted. If current trends continue, they may discover thousands of bright, early galaxies, each one potentially forcing further revisions to our models of cosmic evolution. The statistical power of such a large sample could finally determine whether we are witnessing genuine departures from theoretical predictions or simply the extreme but expected outcomes of known physical processes. But perhaps more importantly, these observations might reveal patterns that point toward the nested cosmic hierarchy that some theories now suggest. If galaxies show coordinated properties across vast distances and cosmic time, it could provide the first direct evidence that our universe participates in organizational structures that transcend our local space-time. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away. Each new discovery chips away at the assumption that our universe is an isolated system, revealing instead a cosmos that might be intimately connected to larger realities through quantum mechanical processes we are only beginning to understand. The search for population 3 stars continues, promising to reveal how the universe's first lights emerged from the primordial darkness. These cosmic pioneers could provide the missing link between the simple universe of the Big Bang and the complex chemistry required for planets and life. Advanced computer simulations running on the world's most powerful supercomputers are being designed to test whether the nested black hole universe theory can quantitatively explain the rapid formation of the early galaxies. If successful, these models could provide a new framework for understanding cosmic evolution that extends from the quantum scales to infinite hierarchies of nested realities. The implications reach far beyond astronomy. If our universe exists within a cosmic hierarchy, then every field of human knowledge, from physics to philosophy, from biology to consciousness studies, will need to be reconsidered in light of our interconnected cosmic status. Future generations might look back on this era as the moment when humanity first began to understand its true place in the infinite network of nested universes. The ancient galaxies that so surprised astronomers could be remembered as the first evidence that reality is far more vast, complex, and interconnected than anyone had dared to imagine. As we continue to decode the messages written in ancient starlight, we might be simultaneously learning to participate more consciously in the cosmic conversation that spans the multiple levels of reality. The universe is not just something we study. It might be something we help to create through the very act of understanding. We began this journey with a single point of light in the cosmic darkness. A galaxy so distant and ancient that it challenged everything we thought we knew about the universe's earliest chapters. Jade's GS Z140, shining across 13.5 billion years of space and time, became our gateway into mysteries that stretch from the quantum realm to infinite cosmic hierarchies. What started as an astronomical discovery evolved into questions about the very nature of reality itself. The galaxy that was supposed to be impossible turned out to be just the beginning, its brightness without a central black hole, its sophisticated chemistry appearing impossibly early, its membership in a growing population of ancient cosmic giants, all pointed toward a universe far more dynamic and interconnected than our theories had predicted. Each revelation built upon the last. Missing supermassive black holes led to questions about feedback mechanisms. Rapid chemical evolution challenged our understanding of stellar life cycles. The abundance of bright early galaxies suggested that dark matter and cosmic structure formation operated differently than we assume. But perhaps most profound of all was the growing evidence that galaxies across vast distances rotate in coordinated patterns, as if responding to some universal organizing principle that extends beyond local gravitational interactions. This cosmic choreography opened the door to the most radical possibility of all, that our entire universe exists within a black hole in a larger parent cosmos. The implications cascade through every aspect of our understanding. If universes reproduce through black hole formation, then consciousness might play a fundamental role in cosmic evolution. The fine-tuning of physical constants could reflect an inheritance from successful parent universes. The rapid formation of early galaxies could express organizational templates encoded during our cosmic birth. We might inhabit not a unique, isolated universe, but one branch of an infinite tree of nested realities, each level contributing to a cosmic conversation that spans scales from the quantum to the infinite. Our scientific observations, our technological achievements, our very existence as conscious beings could be participating in information processing that operates across multiple levels of this vast hierarchy. The ancient galaxies discovered by Webb represent more than distant stellar nurseries. They are messengers from our cosmic dawn, carrying encoded information about our universe's ancestry and its place in the larger scheme of reality. Each photon that traveled billions of years to reach our telescopes might be part of a cosmic communication network that connects nested universes across infinite scales. As we stand on the threshold of even greater discoveries, we face a choice about how to interpret the evidence. We can cling to models that treat our universe as an isolated system, explaining away each anomaly with increasingly complex theoretical patches. Or we can embrace the possibility that reality is far stranger, more beautiful, and more interconnected than we ever imagined. The universe is not just something we study. It might be something we help to create through the very act of understanding. The endless frontier of cosmic discovery stretches ahead, promising revelations that could transform not just astronomy, but our entire conception of what it means to exist in a reality that may be infinite in its depth, complexity, and wonder.